Hello everyone, welcome to Chemazon-Complete Chemistry. So in today's video, we are going to see some of the factors that affect the stretching frequency, that is polarity, bond order, conjugation, percentage as character, hydrogen bonding and reduced mass. So all these are the factors that affect the stretching frequency. So let us see one by one. So the most fundamental law that we had seen in the previous videos is what? Hooke's law. So we are going to make use of Hooke's law to understand the factors that affect the stretching frequency. So you can see nu bar is the stretching frequency. Nu bar is directly proportional to K, that is the force constant. Okay, and this force constant, it is what? It is directly proportional to the bond strength. Okay, it is directly proportional to bond strength, and this bond strength is directly proportional to the percentage S character. Okay, so let us first try to understand what exactly is a percentage S character. So how do you calculate percentage S character? Percentage S character is equal to number of S orbitals divided by total orbitals, okay, divided by total orbitals multiplied by 100. Now from this relation what I have given you, that greater will be the percentage S character, more will be the stretching frequency, that is more will be the bond strength, and bond strength is directly proportional to force constant. So force constant will be higher, so the stretching frequency will be higher. So in short we can say stretching frequency is what? Directly proportional to the percentage S character. Now why this is there? Because the reason is very simple. The s orbital, we know it is closest to the nucleus. S orbital is closer to the nucleus as compared to p orbital, and hence the nuclear charge or the nuclear attraction, or we can say nuclear pull from the nucleus of an atom is very high, since the s orbital is closest to the nucleus. So that is why the bond formed is what? It is a strong bond, or we can say stiffer bond is formed when there is high percent s character. Okay. So now how do you calculate percentage as character, that we have to see. So we have, let's say, three hybridizations. The most common ones are sp3, that is for carbon carbon single bond. Then there is sp2, we know this is for carbon carbon double bond. And then there is sp, that is for carbon carbon triple bond alkynes. So how do you calculate percentage as character? Number of s orbital here is 1. Total orbitals is 1 plus 3 4 into 100. So this will be 25 into 100, that is 20, 0.25 into 100, that is 25%. In sp2 it will be 1 s orbital, total there are 3 into 100, so 33% s character, 33.33. And in sp there is 1 s orbital, total there are 2 orbitals, 1s and 1p, into 100. So here there is 50% s character. Okay, so you can see for a triple bond, that is here there are 3 bonds that are to be broken. Okay, and this bond strength is also directly proportional to, we can say, bond energy. Okay, greater is the number of bonds, greater will be the bond strength, and more will be the bond energy as well, that is the energy required to break the bonds. So energy required to break 3 bonds will be more as compared to breaking 2 bonds, as compared to breaking 1 bond. So the bond order, if we say, it is carbon carbon triple bond greater than carbon carbon double bond greater than carbon carbon single bond. So here you can see the percentage S character is maximum 50%, and the bond, there are multiple 3 bonds are present, so bond energy is maximum, so the stretching frequency for this multiple bond will be maximum. Okay, so in this way we compare the percentage S character to the stretching frequency. Okay, now let us see some values. Okay, bond order is directly proportional to bond energy. We had already seen this, because more energy will be required to break 3 bonds as compared to a single bond. Okay, carbon carbon triple bond is greater than carbon carbon double bond is greater than carbon carbon single bond. This will be the order of stretching frequency. Okay, let us see the exact values. So here you can see carbon carbon single bond, the stretching frequency is minimum. Okay, stretching frequency is minimum 1200, And for carbon-carbon double bond, the stretching frequency is slightly higher. And for carbon-carbon triple bond, here there are 3 bonds. So it is maximum 2200 centimeter inverse. So as the number of bonds or bond order increases, stretching frequency increases. That is what stretching frequency is also directly proportional to bond energy. Okay, so frequency increases with bond energy. Next, again here the same concept is applied. Instead of carbon-carbon bond, here we have carbon-nitrogen bond, carbon-nitrogen single bond, carbon-nitrogen double bond, and carbon-nitrogen triple bond. Again, you can see the stretching frequency is increasing. 1200, then two bonds it is 1650, then carbon-carbon triple bond it is 2200. Okay, so this was okay. One more example: carbon-oxygen single bond, carbon-oxygen double bond. Carbon oxygen single bond it is lower, carbon oxygen double bond it is higher. So I hope you have understood this first factor. Now the next one is reduced mass. So from the Hooke's law, you can see Hooke's law is 1 by 2 pi c root of k by mu. So you can see the stretching frequency is what? Inversely proportional to the root of reduced mass. And reduced mass, we know, we had seen the formula, it is m1 m2 divided by m1 plus m2. Okay, that is m1 is what? M1 m2 is the mass of any two atoms that form the bond. Okay, so suppose I take this bond, hydrogen hydrogen bond, and let's say I take chlorine chlorine bond. So hydrogen hydrogen bond, or let's say I take HCl. So if I compare these two bonds, if I want to find out the reduced mass, you can see hydrogen is same in both the cases. One of the hydrogen is same. Other atom, here there is hydrogen and here there is Cl. So as you increase the mass, what will happen is mu for HCl, we will see it is higher as compared to mu for H2. So stretching frequency is inversely proportional. So higher stretching frequency for HCl, higher reduced mass for HCl, that means stretching frequency of HCl is what? Lower than the stretching frequency of H2. Okay, and how do you calculate reduced mass? Reduced mass will be for H2. If I want to calculate, atomic mass of hydrogen is 1. So 1 into 1 divided by 1 plus 1. So this will be 1 divided by 1, that is 1. And for HCl, mu of HCl, okay, this is H2. HCl will be 35.5, that is for Cl, into 1 divided by 35.5 plus 1. So this will be 35.5 divided by 36.5. So you can see the denominator is higher. So obviously this value will be less than 1. Okay, so in this way the reduced mass of HCl is less than hydrogen. Okay, so this was for HCl. Suppose I take some other bonds. Let's say I take hydrogen hydrogen, hydrogen Cl, hydrogen Br, and hydrogen iodine. So again, as we know that suppose instead of hydrogen I take fluorine. Okay, so fluorine, chlorine, bromine, iodine, as we go down the group, what happens? Atomic number increases, and what will happen? Mass also increases. So mass of iodine is the maximum. So the reduced mass of Hi will be maximum. So what will be the order of reduced mass here? The order of reduced mass will be Hi greater than Hbr greater than HCl greater than HF. So what will be the order of stretching frequency? It is inversely proportional. So the order will be reverse. HF greater than HCl greater than HBr greater than Hi. Okay. So this is the order of the stretching frequency based on the reduced mass. So let us see the actual values now. So here you can see that as the mass of the other atom is increased from hydrogen to carbon, hydrogen atomic mass is 1, deuterium it is 2, carbon it is 12. Okay, so you can see as the mass is increased, the stretching frequency is what? It is decreasing, because we saw just now the stretching frequency is inversely proportional to the reduced mass. Okay, so the stretching frequency decreases as the mass increases. Mass is increasing, that means the value of reduced mass will increase. Okay, reduced mass increases, stretching frequency decreases. So this was the second factor. The third one is conjugation. Now conjugation, if you see a carbon-carbon double bond, that is an isolated bond, let's say ethene. Okay, let's say for this stretching frequency is nu bar 1. Okay, and let's say there is another compound CH2 double bond CH double bond CH2. For this, let's say stretching frequency is nu 2. And then there is benzene. Okay, for this, let's say the stretching frequency is nu 3. So what happens is, you will see in isolated double bond, here double bond is what? It is intact. Okay, it is not lost. The bond order is the same. That is, there are two bonds. There is no resonance. Okay, no resonance possible here. Okay, for resonance, what we want? We want conjugation, that is alternate double and single bond. Like for example, in this case, okay, here the resonance will be possible in 1,3-butadiene. If I write down the resonance structure, what will happen is, okay, here CH2 plus CH double bond CH, okay, CH2 minus. Okay, so this was the resonance structure. Suppose I want to write down the resonance hybrid. Okay, so what will be the resonance hybrid? All the sigma bonds I will keep as it is, and the remaining conjugated part I will show with the help of a double bond. So you can see initially which was a double bond is now become a partial double bond. Partial double bond means bond order is increased, bond order is decreased. A partial double bond means we can say it has got a single bond character, that is bond order is decreased, single bond character. It is not a complete double bond, neither a complete single bond, but you can see clearly that the bond order is decreased. Okay, initially it was a complete double bond, here you can see it has become a single bond, but the resonance hybrid shows that it will be a partial double bond, that is single bond. So we know stretching frequency is what? Directly proportional to bond order, that is bond order is directly proportional to bond strength. Okay, so bond order is, so what has happened here is bond order is decreased, right? Bond order is decreased, so the stretching frequency will increase. Sorry, bond order is decreased and it is directly proportional, so stretching frequency will also decrease. So as the conjugation increases, here there was no conjugation, here there are two pi bonds in conjugation. In benzene, if you see, there are 3 pi bonds that will be involved in resonance, like this. Okay, so if I compare nu 3, nu 2 and nu 1, nu 3 will be minimum, stretching frequency 2 will be less, and stretching frequency 1 will be maximum, because here the double bond is remaining as double bond. Bond order is not decreasing. Okay, so this will be the stretching frequency. Now another example is in the carbonyl compound. Suppose I take one example, that is acetone. Here the stretching frequency is around 1710 to 1720 centimeter inverse. And now if I introduce conjugation, what will happen is, okay, so here what is happening is, you can see here again same concept is happening, that the conjugation is taking place. So here we are talking about the stretching frequency of carbonyl group. So if I draw the resonance, you will see CH2 double bond has now become single bond, CH double bond CO minus 3 lone pairs minus and CH3. So you can see carbonyl stretching frequency has changed from a double bond to a carbon oxygen single bond, that is bond order is decreased, so stretching frequency will also decrease. Okay, so this was another example of conjugation where the electrons are being donated. Okay, one more example is what we can understand is, okay, what will happen is, okay, so this is a table for the first example that I had told you, that if there is an isolated carbon-carbon double bond, stretching frequency is maximum 1640 to 1680. If it is conjugated, that is 1,3-butadiene, it will be slightly lower, and for aromatic carbon-carbon double bond, it is minimum, because 3 pi bonds are involved in resonance. Okay, so now let us try to understand if there is an electron withdrawing group that is present. Okay, if there is electron withdrawing group that is present. Suppose I have one example. Let's say again I take acetone. And now what I will do is at the alpha position I attach an electron withdrawing nitro group. Okay, electron withdrawing nitro group. C double bond O CH3. Again we are comparing what? Which bond we are comparing, that is very important. We are comparing the carbonyl bond. So now what will happen is, now nitro group is what? It is it shows minus R effect, resonance. Okay, electron, it is an electron withdrawing group. Why? Because of oxygen is more electronegative. So what will happen is this oxygen will pull this pi electrons, and in turn what will happen is this is an electron withdrawing group. So there will be electron withdrawing effect, that is minus I inductive effect will also work. And what will happen is this carbon oxygen double bond will now get a what? It will get a triple bond character. Okay, now it will get what? It will get a triple bond character. So initially it was a double bond. Now after this inductive effect you will see that now it has become a triple bond character. It is getting a triple bond character. Okay, after attachment of a electron withdrawing group like nitro. So here what will happen? Let's say this is nu1 and this is nu2. So which one will be higher? Here bond order is higher. So in case of the second compound, that is where nitro group is attached, the stretching frequency will be higher as compared to the acetone group. As compared to this, for this it was nu1. Okay, so nu2 will be greater than, here this is nu2. Nu2 will be greater than nu. So I hope you have understood this third factor, that is resonance. Next is percentage S character. Percentage S character we had seen just now. Nu bar is directly proportional to the force constant, which is directly proportional to the bond strength. And bond strength is what? Bond strength is directly proportional to percentage S character. In percentage S character we had seen in case of SP, it was maximum. Then in case of SP2 it was slightly lower, and in case of, that is 33%, here it was 50%, here it was 33%, and it will be minimum in case of SP3 hybridized carbon, that is 25%. So accordingly, if you see the stretching frequency of this CH bonds, okay, that is what we have to see. For SP3 For sp3 hybridized carbon, this is what? This is sp3 hybridized carbon. This is sp2. This is sp. We know what do we count here? We count the number of sigma bonds plus lone pair not involved in resonance. Okay, this we had seen in the video of hybridization in organic compounds. So here you can see percentage S character. Here it is 25%. Here it is 33%. And in sp here it is 50%. So here percentage S character is maximum. So the stretching frequency of this CH bond is what? It is maximum. sp2 CH bond, it is what? It is slightly less. It is around 3000 to 3100. And of alkane we had seen it is slightly lower than 3000. That is what? That is around 2800 to 3000 centimeter inverse. Okay, so this was about the percentage S character. Next is polarity of the bonds. This also we had seen in the previous video, that the stretching frequency is directly proportional to the change in the dipole moment. Okay, change in the dipole moment. And when this change is maximum, when a polar bond is present, this is directly proportional to the polarity of the bond. So we know that the stretching frequency is directly proportional to the change in dipole moment, which is directly proportional to polarity. Let's say for example OH bond and CH bond. We know OH stretching frequency we see at around 3300 centimeter inverse, and CH we see at around 2900 centimeter. So this is what? This is more polar. And CH bond is what? It is less polar. So its stretching frequency is also lower. Okay, so this was the fifth factor, and last very important factor is hydrogen bonding. So first of all, let us understand what exactly is hydrogen bonding. So it is a bond formed between hydrogen, that is less electronegative, and another more electronegative atom. Okay, this will be delta plus, this will be delta minus. This is more electronegative atom having lone pair. Okay, having lone pair that can interact. Okay, hydrogen can form hydrogen bond with either oxygen, nitrogen or fluorine. Only these three atoms, because these are the most electronegative atoms. Okay, so this was a hydrogen bonding. What are the other examples of hydrogen bonding? Alcohol and carboxylic acid. In carboxylic acid, it forms a dimer, that is two molecules are associating. And alcohol also, you can see this dotted lines represents what? Intermolecular hydrogen bonding. So how does this affect the stretching frequency? So because of this hydrogen bond, what exactly happens is this OH bond becomes weaker. Okay, that is the bond strength of the OH bond decreases. Okay, bond strength decreases. So we know that stretching frequency is directly proportional to K root of force constant, which is directly proportional to the bond strength. Okay, so bond is becoming weaker. OH bond is becoming weaker. So what will happen? The bond strength is decreasing. If bond strength is decreasing, so nu bar will decrease. So what will happen if I compare OH where there is no hydrogen bonding will be stronger. That is, stretching frequency of this where there is no hydrogen bonding will be greater as compared to OH bond where there is hydrogen bonding is present. Okay, because due to hydrogen bonding, OH bond becomes weaker. So hydrogen bonding is present. So where there is no hydrogen bonding, stretching frequency will be higher. And where there is hydrogen bonding present, there the stretching frequency will be lower. Let us understand this with the help of an example. So this is BHT molecule. What is this? Butylated, okay, hydroxytoluene. Okay, what is toluene? Benzene, okay, with methyl group. This is toluene. Then at the para position, hydroxy means OH and butylated means tertiary butyl groups are attached at the ortho position of OH. So here, because of this bulky tertiary butyl groups, what will happen? There is no hydrogen bonding. Okay, although OH group is present, here there is no hydrogen bonding because of steric repulsions, or we can say steric strain. Okay, we had learned the types of strain that we had learned steric strain or van der Waals strain. So because of steric strain or electronic repulsions due to steric hindrance, what will happen? Here there is no hydrogen bonding. So the OH bond is stronger. So you can see the peak of OH is seen at 3600. And you can notice it is a sharp peak. So always remember, whenever for alcohol you get a sharp peak at 3600, you have to understand that there is no hydrogen bonding that is taking place. Okay, and when there is hydrogen bonding taking place, like in paracetamol, here you can see this green one is the intermolecular hydrogen bond. So here what will happen? This OH bond becomes weaker. So the stretching frequency will be lower. We know we get a broad peak at around 3300 centimeter inverse. That is lower. Why? Because the bond strength is decreased, so the stretching frequency will also decrease. So this was the last factor, and I hope you have understood all the 6 different factors that affect the stretching frequency. Thank you.